Hi, everybody. Welcome to Lesson 3, Populations. In the last two lessons, we've really been diving into what an ecosystem is and what it is made up of, with the last lesson being specifically on how does everything in an ecosystem live, a very large picture. This week, we're going to narrow it down just a little bit. We're going to focus specifically on populations, or all members of the same species. For this lesson, if you find it is helpful to think of humans, then by all means think of humans, but understand that this concept is not human specific. It applies to all members of all populations. So dogs, cats, sheep, wolves, bears, etc. Okay. This week, we're going to focus on two ideas. We're going to focus on number one, how do populations change size? They don't stay the same. It's a constantly changing process. And then what factors make population growth stop, or also an opposite, expand or increase? So today, specifically, understanding that populations change size. So there's some very smart people out there. They're ecologists or scientists that focus specifically in the field of ecology. Wow, I apologize. And they really look at the biotic and abiotic factors, remember, living and non-living factors of an ecosystem and how everything just kind of works together. It's like a really good soup. Everything has its own part and it affects everything. I'm really hungry, if you couldn't tell, I'm sorry. But of the scientists that study this wonderful soup, there are some that specifically focus on the idea of populations. And they put to words concepts that we've already kind of known, but they made it scientific. And we understand now that populations change in size, and there's two main reasons why they change. New members join the population, or when members leave the population. And there's two ways that can happen for both joining and leaving. So I want to talk about pair number one, because those two ways are in pairs. The first way population changes size is the natural way, when something is born or when something dies. Now, every time a population gets bigger, it's because, well, I shouldn't say every time. A population naturally gets bigger when something is born. Think about this in your own house. Could have been a family of 3, and then all along comes little brother or sister here to ruin your world, right? And your population has grown to 4 people. Or the opposite. You have a family of 8 people. Unfortunately, somebody dies. Well, that population's gotten smaller. And we track both of these by using rates. Now, you'll learn more about rates in math, but we use rates to determine how quickly or how slowly something changes. In this case, birth rate tells us how quickly the population is increasing. Death rate does the opposite, how quickly the population is decreasing. Now, using birth rate and death rate, there are 3 different scenarios that affect our population. If the birth rate and the death rate are the same, +5, -5, they balance out and the population remains the same. Can you think of the other two? Well, the next one is if the birth rate is larger than the death rate. And this is what's been happening on planet Earth for humans specifically, well over the last 300 years. When the birth rate exceeds the death rate, we're going to find that our population goes up. Likewise, if the death rate is larger than the birth rate is smaller, then our population is going to decrease. Now, those are 3 concepts that we can use to apply to what is actually happening in our planet. Now, this chart shows population growth for the last 300 years and a prediction for the next 100. Well, at this point, 80, but you know what I mean. We look back in 1700, the population was 600 million people, and that's for the entire world. It took 100 years to break 1 billion people. In the 1800s, we broke 1 billion people. Another 128 years, we grew another 1 billion people. So for there, the birth rate and the death rate were very close, the birth rate being just slightly larger because of a very slow population increase. And you can see that with this purple line right here. Now, 1928 is when things get interesting. You can see that our growth rate skyrockets. And it skyrockets. There's a lot of things that are going on in history, but a lot of it's going on because of World War I and World War II. World War I just ended. World War II ends here in 1950. And you can see from here, and then all of a sudden, it literally takes off like a rocket right here. We have the baby boomer generation, in which everybody came back from the war in 1945, and they started having babies. It was a boom in the population, hence the phrase baby boomer. There's actual scientific reasoning behind it, ladies and gentlemen. Anyways, as you can see, the best year ever, 1987, my personal year, we're continuing to skyrocket. This is when the birth rate far exceeds the death rate. And part of it is because also during this time, medicine got better. So people started living a longer life. So people living longer, plus more people being born, less people dying, huge skyrocket in our population. We'll talk about this part here tomorrow as to why we start to see the decrease. It's interesting, I promise. The second way, however, and the population change in size is also another relationship, and it's the idea of migration. Now I'm saying migration with an M. I'm this part right here, migration. Excuse me. Migration is the referring to organisms moving place to place. Not just humans, everybody migrates, everything migrates. Now, well, plants don't, but anyways, when we're talking about immigration, we're talking about a specific form of migration in which a member moves into a population. Well, how do you remember immigration being into? Well, they both start with an I. Okay, that's my cheaty way. Likewise, if an organism emigrates, they're going to exit the population and move somewhere else. There's a lot of reasons why organisms immigrate and emigrate, or for simplicity's sake, there's a lot of reasons why migration happens, and we'll talk about those tomorrow as well. The last thing that we need to talk about, we talked about how populations change in size, right? So we need to make sure we understand, how do we discuss what a population looks like now in terms of population or the numbers? And that's what we use a term called population density. Now, if we're talking about density, we're talking about how tightly packed something is. So when we're talking about population density, we're talking about how tightly packed something is in terms of specific organisms. Your best example would probably be that of a classroom. You've had classes where you've had small class numbers and large class numbers, and that's a perfect representation of why, we need to understand this. If you had a class of 20 students versus a class of 34 students, well, there's pros and cons to both, but me personally, I would choose to be in the 20. Why? Because the teacher's going to know who I am. The teacher's going to be able to help me. Whereas in the 34, there's a lot of things in that specific area. So we have two examples here of population density: very low population density, a very high population density. And there's a mathematical formula that we can use to find what that density is. Number of individuals, in this case, we have 10 flamingos divided by a specific area. Well, the area of this rectangle is 8 meters. 10 divided by 8, I have a population density of 1.25 flamingos, about 1 flamingo per meter right here, okay? That's not right. No, that is right. I'm right. I'm sorry. Whereas down here, 5, 6, 7, 8, 9, 10, we're going to say 20 flamingo, same area, but we're looking at about 2.5 flamingo per meter now. So we've doubled this, and it's a lot more crowded. So this is going to be really important because this directly leads into what we talk about tomorrow. I hope you understood the concepts. If you didn't, feel free to ask me a question. Send me a message, leave a comment, do what we need to. Until then, have a good one. Bye.